You know, for years, the mantra in AI has been pretty simple. Just make it bigger. Bigger models, more data, more power. But what happens when bigger just gets way too expensive and, frankly, too inefficient? We're kind of hitting a wall. So the race is on to figure out how to make AI not just bigger, but fundamentally smarter. And that's exactly what we're going to dig into today.
And that really gets us to the heart of the problem this research is trying to solve. I mean, it's a classic engineering challenge, right? How do you squeeze out more performance without just throwing an endless pile of money and resources at it? The cost to train and run the top AI models today is just staggering, so finding a more efficient way forward is absolutely crucial.
So the way we've traditionally done things is with what's called a dense model. Picture this. It's like a single giant brain where every single neuron has to fire for every single thought. It's powerful for sure, but it's a total brute force approach. And as you try to make that brain bigger to learn more stuff, the energy it takes to even think just becomes astronomical. That's the bottleneck we have to break.
All right, so here's the game plan for today. First, we're going to really break down this AI scaling problem. Then, we'll look at a really clever workaround that's been gaining steam known as mixture of experts. And that's going to lead us right to the main event, this radical new architecture called PEER. We'll see how it holds up under pressure, and finally, we'll talk about what a future with 1 million experts could really unlock for AI.
Okay, let's dive right in. First up, the AI scaling problem. I mean, the whole bigger is better philosophy has gotten us pretty far, but we're starting to see that it has some very real, very hard limits. So to really get this, we've got to peek under the hood of these AI models we use every day, transformers. Inside them, you've got these things called feed-forward layers. Think of them as the model's long-term memory, where all its knowledge is stored. But here's the kicker. They make up a massive 2/3 of the entire model's size. That means every time you want to add more knowledge, you're paying this huge computational tax.
You know, this whole cost issue got researchers thinking there has to be a smarter way. Instead of one giant brain doing all the work, what if you had a whole team of specialists? And that's the core idea behind what we call expert models.
This is where we get to something called mixture of experts, or MOE for short. The idea is, instead of that one massive, dense layer, you break it up into lots of smaller expert networks. When a question comes in, a little routing system figures out which one or two experts are the best to handle it. It's literally like having a committee of specialists. You wouldn't ask a physicist for legal advice, right? You just go to the lawyer. It saves everyone else's time and energy. So when you put them side by side, the difference is just, well, it's night and day. The dense model is that one genius trying to think about absolutely everything at once. It's incredibly inefficient. The MOE model, on the other hand, is that team of specialists. And what this does, and this is the key breakthrough, is it decouples the size of the model from the cost of running it. That's what makes models with trillions of parameters even possible.
Okay, and this is where things get really interesting. This new research takes that whole MOE idea and just cranks it up to 11. It's like going from a small committee of experts to a sprawling, bustling city of them.
There's a quote from the paper that just perfectly captures their core idea. It says, "Continued improvement of model capacity will ultimately lead to an immense number of tiny experts." So they're not just thinking about a few hundred experts. They're predicting a future built on millions, or maybe even billions, of tiny, super specialized little knowledge bits.
But of course, that creates a brand new problem. And it's a huge one. I mean, finding the right two specialists out of, say, 128, that's manageable. But trying to find the best expert from a pool of over 1 million? A simple search would be computationally impossible. It would actually be slower than the dense model we were trying to get away from in the first place.
And this is where their big solution comes into play. PEER, which stands for Parameter Efficient Expert Retrieval. It's a whole new system designed specifically to solve this gigantic search problem. The secret sauce is this really clever technique they call product key retrieval, which lets the model's router find the perfect expert out of millions without having to check every single one.
Okay, so how does this actually work? Because it's pretty brilliant. Imagine you've got your million experts laid out in a giant grid, say 1,000 by 1,000. Instead of searching all 1 million squares on that grid, what you do is you search the 1,000 rows, and then you search the 1,000 columns separately. That gives you a much, much smaller set of possible intersections to check. It basically reduces a search of 1 million items down to a search of just 2,000. It makes the impossible possible.
So the idea is fantastic, right? But the real question is, does it actually work in practice? Let's move on and look at the proof.
Okay, what you're looking at here is something called an isoflop chart. It's just a fancy way of saying if we give each model the same amount of computer power, who does a better job? We're measuring something called perplexity, which is basically a score for how good the model is at predicting the next word. All you need to know is lower is better. And as you can plainly see, that teal line representing peer is consistently the lowest. For the exact same compute budget, peer is just a smarter, more capable model.
And if the chart wasn't clear enough, the numbers here in this table really drive the point home. Just look at that bottom row. On two different big data sets, C4 and the pile, peer gets the lowest perplexity, the best score, using the exact same amount of compute as the other models. It's not just a tiny bit better, it's a really significant jump in efficiency.
And this chart here, this is kind of the final nail in the coffin, the ultimate proof. The researchers tested what happens as you keep adding more and more experts, starting from around 16,000 all the way up to over 1 million. And the result? The performance just keeps getting better and better. It's a straight line up. This confirms their core idea. More tiny experts really does lead to a better model.
All right, so we've seen that it works. But what does this actually mean for the future of AI? This isn't just a small step. It could be a whole new path forward for how we build and scale these massive models.
So the big takeaways right off the bat are pretty clear. We've now got a much more efficient way to scale up our biggest foundation models. But where it gets really mind-bending is the long-term potential. I mean, think about lifelong learning. Right now, if you try to teach an AI something new, it can sometimes forget what it already knew. They call it catastrophic forgetting. But with an architecture like this, you could potentially just add new experts to teach it new skills without having to retrain the entire thing from scratch. This is a real potential pathway to an AI that can constantly grow and adapt over time.
And that really is the big question this research leaves us with. They've proved the principle works for 1 million experts, but the technique itself is scalable. So what new incredible capabilities might pop up when we can build models that have 1 billion or maybe even 1 trillion specialized little experts to call upon for any task? That's the future this research is pointing towards.
This is for entertainment purposes only.